is expected to dissolve this bound state, leading to a suppression in a process which is called color screening. In this process, the C and C bar quarks produced in the initial stages get screened with the gluons and the light quarks in the gas, and they end up hadronizing with light quarks forming the mesons. But the process, it's more complex than just this, because Jeb size suppression can also be produced in a process which is called commuter scattering, in which after hadronization, the Jeb size can interact with the light mesons of the gas and producing the mesons. And this can happen if the quark-gluon plasma has been produced, but also if it hasn't been produced. So in order to understand the modification of Jeb size and charmonia, it is also interesting to understand the modification of open char mesons with temperatures, because if their masses and width change with respect to their vacuum values, also the threshold for this commuter scattering will change, and it will have consequences for Jeb size suppression. The properties of hadrons, like their mass and widths, are contained in their spectral functions. Therefore, the study of these spectral functions with temperature will allow us to extract thermal modification of hadrons. We use a unitarized approach based on an effective hadronic theory to calculate the spectral functions of heavy mesons. And we study matter at high temperature below Tc and at vanishing baryon density. And in this regime, matter is composed of mesons that are thermally distributed. Because of the interaction with the medium, the ground state open char mesons modify their masses and widths. And as a consequence of this, also the properties of the excited mesonic states that are dynamically generated by the model, such as the D2300 or the D12430 or the strange DS2317 or DS12460. These dynamically generated states will also change with temperature, as I will show later in this talk. And also the calculation of spectral functions can be computed in our model at unphysical masses in order to calculate Euclidean correlators that then we can directly compare with lattice QCD calculations. So I start with the molecular model. The constituent quarks, the basic constituents in QCD are quarks and gluons, and the conventional quark model has been successful in describing the hadron structure for many years by only considering colorless combinations of three quarks, the baryons, and quark-antiquark, the mesons. But with the time, many excited hadrons have been discovered that do not accommodate in this simple QQQ or QQ bar picture. And these hadrons can be better described by having other configurations that are allowed by QCD, and these configurations are called exotic. Baryons and mesons are not the only colorless configurations of quarks. For instance, in the case of baryonic systems, we can have also 4 quarks and an antiquark, what we call pentaquarks, that can be organized either in a compact pentaquark or in a meson-baryon molecule consisting of a traditional meson and baryon that are loosely joined together. There are some examples of these states that are manifestly exotic, such as the well-studied lambda 1405 or the first evidences of pentaquarks, the PC4380 and 4450, which were discovered by CERN already 5 years ago. But the true nature of their structure, if it's either a pentaquark or a meson-baryon molecule, is still the subject of great theoretical effort. In the case of mesonic states, we can have tetraquarks consisting of 2 quarks and 2 antiquarks, either organized as a compact tetraquark or a meson-meson molecule. But in addition, we can also have the possibility of hybrids in which gluons would also play an important role in addition to quarks. And gluons that would be bound states of gluons only. Hybrids and gluons haven't been discovered experimentally yet, but there are many candidates of tetraquarks, such as the D and DS that I will explore in this, with our models, but also the famous X3872 or the charged charmonium Z states, which by definition have to be exotic. So hadronic molecules can be defined as deuteron-like quasi-bound states of 2 hadrons that they are usually located close to threshold masses, and they are studied using effective hadronic theories in which mesons and baryons are the degrees of freedom. In our case, well, in general, an effective hadronic theory is built by taking the most general effective Lagrangian consistent with the symmetries of the underlying theory. In our case, the underlying theory is QCD, and it has chiral symmetry in the limit of vanishing masses of the up, down, and strange quarks, and in the opposite limit, in the limit of infinitively heavy quarks. QCD has also a symmetry which is spin flavor symmetry. In this effective theory, the new degrees of freedoms are mesons and baryons, and the interaction is mediated by the exchange of mesons. So, taking into account all these considerations, we can obtain the Lagrangian describing the process that we are interested, which is the interaction of the heavy D mesons with the light pseudoscalar mesons. We use a Lagrangian which has been expanded to next to leading order in the chiral expansion, but keeps the leading order in the heavy quark expansion. The leading order Lagrangian is the one that I'm showing here. There are these terms that describe the scattering of the heavy pseudoscalar meson with the light mesons, and these ones in the case of the heavy vector mesons. This Lagrangian is a function of the SU3 anti-triplets of spin 0 D mesons and spin 1 D star mesons, and also of the SU3 matrix containing the Goldstone bosons that enters the Lagrangian through the covariant derivatives here that you see in these terms. The next to leading order part of the Lagrangian contains a few more terms, each of them multiplied by a next to leading order constant, this H0 to 5 for spin 0 D mesons and the H tilde for spin 1 D star mesons. But the number of next to leading order constants is reduced at leading order in heavy quark spin symmetry, because in that case, we have that the H tilde are equal to the H.
Gloria, may I
yes.
ask you something? Which are the expansion parameters or the expansion parameter in your EFT?
The expansion parameters?
Yeah, maybe you said, but maybe I missed it. Yes. So you are expanding leading order, and then next to leading order, what's the expansion parameter that this that
yeah,
you have?
In the chiral expansion is the momentum, and in the heavy quark expansion is the heavy quark mass.
So it's the typical momenta you have is, sorry, maybe this is a basic question. I'm not used to this. I'm used to the nuclear structure sector. So which are the typical momenta that you would have?
I don't know. low momenta. I don't know that. But yeah, usually I mean, I don't do these expansions. We just take the Lagrangian from that has been studied by other people, and we use it and we trust it. So yeah, in the chiral expansion, you
So
do
these are probably then the momenta of the order of the pion mass?
Yeah, probably, because it's in the chiral expansion, and in the heavy quark expansion, you use the mass of the heavy meson. So it's, yeah, the mass of the meson.
Thanks.
Let's see where I was. Here, I think. Okay, so when we work the scattering amplitude for a transition from channel I to channel J, as depicted in this Feynman diagram, the expression that we obtain is the following, that contains a term that comes from the leading order Lagrangian and the rest that come from the next to leading order Lagrangian. And the quantities Cij are the coefficients of the scattering for this particular transition from channel I to channel J, and we take them in isospin basis. And also the low energy constants have been fitted to scattering lengths calculated in lattice QCD by Guo and collaborators. We take the values in this paper. So the next step in the model, once we have defined the interaction, is the unitarization. We use the Bethe-Salpeter approach, which consists in an infinite sum of terms containing increasing number of loops in coupled channels, as diagrammatically depicted in this plot, where the small circle would correspond to the scattering amplitude that I showed in the previous slide, and the dark big red circle is the unitarized amplitude that we call the T matrix. This infinite sum can be rearranged this way. So after on-shell factorization, the T matrix can be obtained by solving this analytical matrix equation. The loop function that enters the Bethe-Salpeter equation is built from the propagators of each of the two mesons, but it needs to be regularized. And there are many approaches to do so. For example, dimensional regularization, which introduces a subtraction constant for each channel K at a regularization scale mu. And the approach that we use is cutoff regularization, which consists in the introduction of a cutoff. But both these approaches can be related by asking that they give the same value of the loop function at threshold. Then out of the T matrix, which would be, for example, this orange line that I show here, one can find the resonances that correspond to heavy light meson molecules that are dynamically generated in our model. And to characterize these resonances, what we do is to perform an analytical continuation to the complex energy plane and identify the poles. This would be this gray plot. And these resonances can be classified into bound states, resonances, or virtual states, depending on the Riemann sheet where they are located. And from the position of the pole, we can obtain the mass of the resonances from the real part and the half width from the imaginary part, but we can also obtain from the residue around the pole the coupling constants, which give us information about the strength of a particular channel in the generation of the resonance, and the compositeness that tell us about the amount of a particular channel in the composition of the resonance. And with this, I come to the first part of the results. Our approach is in coupled channels, and we work in isospin basis. So in these tables, I show the various channels with light pseudoscalar mesons scattering with heavy pseudoscalar mesons on the left and with vector mesons on the right. We find interesting results in the sectors with strangeness 0 and isospin 1.5, where the dynamically and yeah, where the dynamically generated resonances can be identified with experimental states and also in the sector with strangeness 1 and isospin 0. Also, in the case of the vectors, they are experimentally reported states in these sectors. In the case of the scalars, our model is able to dynamically generate the D2300 that has strangeness and isospin quantum numbers equal to 0, 0, 1/2, and it has a double pole structure with a lower resonant pole coupling mostly to d pi, and a virtual pole which is located near the DSK bar threshold in a Riemann sheet, which is not the second Riemann sheet, but it's close to it. And it mostly couples to this channel. In the plot, I show the imaginary part of the T matrix in the diagonal channels for each of these channels, the d pi and DSK bar. And we can see that due to the presence of the thresholds of d eta and DSK bar, the higher resonance suffers from a flatte effect that makes the width much smaller than that of the value that we obtain from the imaginary part, the imaginary position of the pole. And in the sector with strangeness 1 and isospin 0, the DS2317 is generated as a bound state below the DK threshold. The case of the axial vectors, the D12430 and DS12460, is completely analog to the one that I just discussed. The D12430 has a double pole structure, the lowest pole coupling to D star pi and the higher one coupling to DS star k bar. And the DS12460 generated as a bound state. So now I can explain you how we introduced finite temperature in our model. First, a short introduction. At finite temperature, but below the transition temperature, we have a meson gas, in which the abundance of each of the mesons is given by the thermal distribution. So the most abundant mesons are the lightest ones, in this case, the pions, the mass of which is of the order of the temperature. And heavy mesons behave as Brownian particles in this mesonic bath, and the scattering of the mesons with the light mesons can be described with the model that I just explained in the previous slides, but extending it also to include temperature corrections. So what I want to emphasize is that in a thermal bath, new processes that were not accessible in vacuum now become possible. Not only the production of heavy light pairs, but also the absorption of thermal heavy light pairs now becomes possible. So how do we do this? First, we use the imaginary time formalism. Basically, we substitute the zero component of the form momenta with a discrete Matsubara frequency for bosons and the energy integral by a sum over this Matsubara frequency. And second, what we do is dress the propagators of the heavy mesons with the self-energy obtained from closing the pio line in the corresponding T matrix element. I will depict in the diagrams that will follow. When the mesons are dressed, I depict them in colored lines. And in principle, the light meson should also be dressed, but we have checked that the modification of pions with temperature is moderate, and that the effect on the modification of the heavy mesons, that is what we study, is even smaller. But it will be the next step that I will carry out, is the introduction of this, the dressing of the light mesons in my codes. The calculation of the new unitarized scattering amplitude now has to be done in a self-consistent way. First of all, we obtain the loop function by integrating over the spectral functions. with the approximation that we only address the heavy meson, we can simplify this expression by replacing the spectral function of the light meson by a delta function. And this simplifies the calculations, basically. Also from the sum of Matsubara frequencies, we obtain this factor, including meson-Bose distribution functions at temperature T. As in the zero temperature case, we have to regularize the loop, and we do it again with a cutoff. The next step is to unitarize the interaction by solving again the Bethe-Salpeter equation, but now including the dressing of the heavy mesons in the loops. The imaginary part of this T matrix then enters in the expression of the self-energy, weighted also by a combination of Bose distribution functions. And from this self-energy, then we calculate the spectral function for the heavy meson, which is then used to calculate the loop function. So you can see that this procedure needs to be iterated several times to ensure the self-consistency of the results. Okay, this slide is a bit full of equations, but don't scare of it because it's quite simple to understand, and I include it because I want to give a physical interpretation of what is this thermal bath doing. So after some analytical work, one can rewrite the expression that I showed for the loop function as a sum of 4 terms with different combinations of Bose factors in the numerators and different energy denominators. Then it is very easy to relate each term to meson absorption and production processes. For example, if we look at the first term, it might be interpreted as the production of a heavy light pair and an absorption of also a heavy light pair. And the production is weighted by a weight factor given by 1 plus f of the d meson times 1 of the f of the light meson. And the absorption is weighted by a statistical weight factor, which is f of the d times f of the light meson. And similarly, the other terms can also be related to different absorption and production processes of heavy light, quark, and the heavy light particle antiparticles. And I want to note that at 0 temperature, this Bose distribution function is 0. So the only terms that survive in the loop are the production of a heavy light pair and heavy light antipair. And if we now look at the denominators of this expression, we can read out the location of a branch cut located at the channel threshold, which is the standard cut that we have at 0 temperature. But in addition, because we have additional processes, as I said, at finite temperature, a new cut develops at the difference of the masses, the mass of the heavy minus the mass of the light, and this is known as the Landau cut, which is not present at 0 temperature. So I show the results. Here in this slide, I show the loop functions for the d pi on the left and the ds pi channel in the right, the real part in solid lines and the imaginary part in dashed lines for different temperatures going from 0 in black to 150 MeV, which is the highest temperature we consider in orange. And these results correspond to heavy mesons in a pion bath. If we focus on the imaginary part of the d pi, for example, loop function, we can see the right-hand cut at threshold and the left-hand cut at the mass of the d minus the mass of the pion. At finite temperature, these cuts are shifted towards lower energies because, as I will show later, the heavy meson mass gets modified in a pion bath, and also it gets smooth due to the width, which is acquired by this heavy meson. And the left-hand cut in the imaginary part is, and also the modification of the real part in this energy region is also more pronounced with increasing temperature because of the more abundance of pions with larger temperatures. In the case of loops with heavier light mesons, which I'm not showing here, like for example, the loops with the kaon and the eta, the effects of the temperature are less pronounced because the Bose factors for these particles at a given temperature produce smaller contributions. And okay, the loop functions for the vectors, the D star and the DS star with pions, are pretty similar to the ones that I just showed for the pseudoscalars, as one expects from heavy quark symmetry. The only difference is the position of the thresholds, which is given by the masses. Yeah. Okay, now in these plots I show the spectral functions obtained for the D meson on the left and for the DS meson on the right, as a function of the energy for different temperatures. As we can see, the effect of the temperature is basically to shift the mass towards lower energies with increasing temperatures, and also a widening. This widening and the shift of the mass is larger for the D meson because its interaction with the pion mass, with the pion bath, is stronger than in the case of the DS meson. Again, the picture of the spectral functions for the vector mesons is analog to the case of the pseudoscalars. The spectral functions of the D star and the D star. From these spectral functions, we can see the mass shift and widening is very similar in the case of pseudoscalars and vectors. In the case of the dynamically generated resonances, I plot the imaginary part of the D matrix obtained at finite temperature. In the case of strangeness 0 and isospin 1/2, the two peaks of the D2300 are shown in the top panel. It may seem from this plot that the lower resonance moves towards high energies with temperatures, but this is an effect coming from the interaction of the resonance with the background. From the fits of both resonances at different temperatures, we find that the masses decrease with temperatures and their widths increase, but more moderately than in the case of the ground state. In the sector with strangeness 1 and isospin 0, the DS2370 that was generated at 0 temperature as a bound state, we can see that the effect of the temperature is to move the peak to lower energies, and it broadens also significantly. Again, I show the analog case of the dynamically generated axial vectors, and the same discussion that I just did for the D2300 applies for the D12430, and that for the DS2317 to the DS12460. In order to quantify the mass shifts and widenings, I show here in these plots the masses on the left and the widths on the right, obtained for the ground state and spectral functions, and fits in the case of the D matrix for the dynamically generated states. The top plots correspond to the case of non-strange mesons, and the bottom ones in the case of mesons with strangeness. And the solid lines correspond to a thermal bath with pions only, as the plots that I have shown so far. The mass shift for the D meson is of around 40 MeVs at the maximum temperature that we consider, that is 150 MeVs. And the shift of its chiral partners is much moderate. And in the case of the DS, the mass shift is around 20 MeVs, And it is similar for its chiral partner, the DS2317. So we don't see any hint of restoration of chiral symmetry with our model, but we are considering temperatures which are still considerably below the chiral restoration symmetry temperature. And the dashed lines here correspond to the results of the self-consistent procedure when we include, in addition to pions, we include also kaons and antikaons in the bath. That is, in practice, what we do is closing not only the pion line to calculate the self-energy of the heavy mesons, but also the kaon line. And because the abundance of kaons at these temperatures is much less than the abundance of pions, we see that the results of the masses don't change much. The largest effect of the inclusion of kaons that we find is in the width of the DS meson, which is more than twice the width at 150 MeVs when considering a pion bath only, due to the fact that the interactions of the DS with pions are relatively weak, and its interaction with kaons and antikaons is more important. And in the case of the thermal evolution of the masses and widths of the vectors and axial vectors, we observe again a clear parallelism with that obtained for pseudoscalars and scalars, due to the fact that the interactions of pseudoscalars and vectors with light mesons is related by heavy quark spin symmetry.
Gloria, let me ask one question.
Yes.
So you mentioned this restoration of chiral symmetry that you do not observe at 150 MeV. So at which temperature would you expect that? And is it possible with this formalism to get into these temperatures?
Okay, as we, the chiral restoration symmetry is expected to happen at the temperatures around the confinement transition temperature, right, more or less. So yeah, when we approach this temperature, we expect the mesons to start to dissolve. So our model is not valid anymore close to the temperature and obviously above to this temperature where the confined degrees of freedom have to be included. So that's why not observing this chiral restoration symmetry is not that bad, because our model does not include all the ingredients.
Yeah, thank you.
So, okay, with this, I go to the last part of my talk, which is the calculation of Euclidean correlators from open char mesons from spectral functions that we calculate with the formalism that I just discussed, to see how they compare with the Euclidean correlators that they obtain with lattice QCD. Given the spectral function, the Euclidean correlator can be obtained with this relation here, where now I call rho the spectral function. It is basically the convolution of the spectral function with a kernel which is temperature dependent and is given by this expression. The Euclidean correlator is the object that is directly computed in the lattice, but the object that contains information about the mesonic states is the spectral function. So what lattice people have to do is the inverse process, which is a non-trivial task. The inversion of the Euclidean correlator is an ill-posed problem, because what they have is a discrete point in a number of discrete points in Euclidean time with statistical errors, and this is an ill-posed problem. And there are two methods that they usually employ to circumvent this problem, which are Bayesian methods like the maximum entropy method. And also some people feed lattice data with suitable guesses of the spectral functions, but both these methods rely on assumption of the shape of the spectral function. And that's why we want to compare directly with the Euclidean correlators calculated in the lattice. And when directly comparing correlator functions at different temperatures, one wants to separate the different the modification of the spectral function with temperature, the modification of the spectral function itself from the temperature dependence of the kernel that, as I showed here, also depends on temperature. So what one has to define is the reconstructed correlator at a reference temperature TR, which is chosen to correspond to the lowest temperature available. And this is because it is closer to the vacuum spectral function, which is the one which is well known. And then what we compare is ratios of the Euclidean correlator to the reconstructed correlator at different temperatures. With the methodology that I have explained before, from the effective interaction of heavy mesons with light mesons, we obtain the ground state spectral function, right? In this hadronic effective model, the masses of the mesons in vacuum are input parameters, and therefore can be tuned to those used in lattice QCD to do a straightforward comparison of both approaches. But the spectral function rod that I introduced in the equation in the previous slide to calculate the Euclidean correlator has dimensions of energy squared, while our spectral function S has dimensions of 1 over energy squared. The relation between the ground state contribution to rho and S is through the 4th power of the charm meson mass. And in addition to Euclidean, well, the Euclidean correlators also include not only the ground state, but the full spectral function, which is the possibility of having excited states and the continuum of scattering states. As a first approximation, we add a continuum contribution to the ground state, which results from the effective hadronic model. And so in this way, we want to compare with lattice QCD with the fewest difference possible. And the continuum spectral function is sometimes mimicked with a step function, but a better choice is to take a parametrization of the free meson spectral function in the non-interacting limit. In the case of a meson with a light quark and a heavy quark, this is the expression. And M1 is the mass of the heavy quark, in our case the charm, and M2 the mass of the light, which is the up or down for the D mesons, and the S in the case of the DS mesons. And we also introduce a factor A, which weights the contribution of the continuum with respect to the ground state spectral function. So finally, I show results for this part. We have tuned our calculations in order to use the meson masses and the temperatures used in the lattice QCD calculations by Kelly and collaborators, which is, as far as we know, the only work calculating Euclidean correlators and spectral functions of open charm mesons with lattice QCD. Here I show the results of the hadronic theory for the spectral functions of the D on the top and the DS meson on the bottom for the temperatures that have been considered by this work. And although our model is only justified below TC, which in the lattice is calculated to be 185 MeVs, we perform our calculations for temperatures also above this value to see how the results of the hadronic model depart from those of lattice QCD. In these other plots on the right, I show the spectral function rho with the ground state and the addition of the continuum with weight factor A, which is equal to 0, that would be without continuum, and also with A equal to 1 in dashed lines and A equal to 10 in dotted lines. And with each of these spectral functions, what we do is to calculate the Euclidean and the reconstructed correlators. And here I show the results of the ratios in the case of the D meson. On the left, I show the case where we don't consider the continuum, that is the A equal to 0. And on the right, in the case of continuum, equal to 1 in dashed lines and equal to 0 in dotted lines. And together with the lattice data with the error bars. And the very first observation is that there is a large departure of the Euclidean correlators with respect to the lattice data at small values of the Euclidean time tau, when we do not include the continuum. And when we do include the continuum, the ratios go to 1 in the limit of tau going to 0 for all the temperatures, which is the behavior which is observed on lattice QCD data. And this is due to the fact that the small tau region of the Euclidean correlator is sensitive to the spectral function at large energies, where the continuum is located. At larger taus, we get really good matching of our results with those of the lattice for the lowest temperatures, T equal to 141. And at T equal to 156 in blue, our results still lie close to the lattice error bars. At larger temperatures, the behavior of the correlators with both approaches are quite different, but the reason for this departure is not easy to determine, because on the one side, our calculations are missing contributions of excited states that are present in the lattice and which may affect the middle range of taus. We also have to take into account that the effective hadronic theory is not valid close to TC and obviously above TC, where the deconfined degrees of freedom have to be taken into account. And in addition, lattice calculations suffer from cutoff effects due to the finite size of the lattice, which are very difficult to mimic and we haven't considered in our calculations. It would be interesting to have more data at smaller temperatures to check how good are our calculations. But here I show that they are already surprisingly good at 141 MeVs, which is quite high temperature. In the case of the DS meson, only the calculations at the temperatures of 140 MeVs are close to the lattice QCD error bars, but the behavior is very similar to that discussed in the D meson. But here in the case of the D meson, we also have to consider that we didn't consider the kaon induced width, which might improve this comparison. The calculations at unphysical masses are done considering only a pion path, but I have shown in the case of calculations at the physical point that the inclusion of kaons and anti-kaons in addition to pions have a large effect on the width of the DS meson. And this larger width, which is twice as the one we don't consider with only pions at the physical point, might have a large effect. And here, in which with unphysical masses might be even bigger, because the pions are much heavier, so their thermal abundance is closer to the thermal abundance of kaons in this case. So with this, I come to the conclusions. We have introduced finite temperature corrections to the description of the interaction of open char mesons with light mesons in a self-consistent way. And I have shown that we have obtained spectral functions at different temperatures below TC. And the effect that I have shown is that the mass of the charm D and the pseudoscalars D and ds and the vectors D star and ds star is that the mass is decreased with temperatures about 40 MeVs for the D and the D star and about 20 MeVs for the ds and ds star at the highest temperature that we consider, which is 150 MeVs. And they acquire also an important width, around 70 MeVs for the non-strange and 20 MeVs in the case of the strange mesons. And for the dynamically generated resonances, the shifts of the masses are also important, but not as much as in the case of the ground states. And they also get wider with temperature. but I have shown that we are still far from achieving chiral degeneracy. And I have also shown that the addition of kaons in the bath is not that important. It is only quite remarkable for the case of the width of the DS meson. And finally, we have calculated the Euclidean correlators from spectral functions at the unphysical masses using the lattice to directly compare both approaches. And the comparison is quite good below TC, and above TC, the discrepancy could indicate that we are missing, for example, contributions of higher excited states. And in the near future, what we will do is to include the modifications of the light mesons. As I said, this is numerically very challenging because when considering a delta function for the spectral function of the light mesons, we get rid of an integration. So we have to include one more integration in our codes, and this is a challenge. And we also want to extend our calculations to the bottom sector and also to the hidden heavy flavor sector for charmonia and also for botomonia. And we are also studying transport properties of heavy mesons at finite temperatures. And of course, we want to further test our results against lattice QCD calculations, either for the open heavy flavor if there are more calculations on the lattice, or with the heavy flavor sector when we obtain results for that sector, and also make predictions of what they could obtain on the lattice at the physical point. So that's all. Thank you.
Thank you very much, Gloria, for the very nice talk. And now we have some time for questions. So you can, yeah. Arnau is asking whether you can comment on the cutoff dependence of your results.
Okay, I guess he wants to know what is the effect of the cutoff when we introduce this regularization scheme for the loop function calculation. We haven't explored the modifications, but with this cutoff, we reproduce basically the experimental states. We are basing our calculations on the effective potential with the low energy constants fitted to lattice data, and in that work they use the dimensional regularization scheme, and we have checked that using our cutoff, we still reproduce this lattice data and everything. So, I mean, yeah, this cutoff is basically fixed at vacuum. It's basically used to fix our model at 0 temperature and to reproduce all the data, the dynamic regenerated resonances, and also the scattering lengths that come from lattice QCD. And we just take the same value to extend our model to finite temperature. But I mean, it doesn't really make sense to change it to different values because we wouldn't be able then to reproduce the data that we want to reproduce.
I see. So just to follow up with Arnau's question. So this is something that you do not have the freedom to vary, and then it wouldn't be useful to do this variation in order to get some uncertainties of your calculation. Then you say that this doesn't really make sense in your case.
Yeah, probably you would get results that are farther away from the experimental and the lattice data. So I mean, it makes sense to explore a bit the dependence at 0 temperature, which has been done by many people. And in the end, they fit the values, taking a cutoff, which is a physically justified value, which we take it of 800 MeVs. And yeah, it's about the mass of the meson, which can be in when in the transition, the mass of the mesons that can be exchanged is of that order. So physically, also it's the value that usually people use, and it also reproduces the data. And yeah.
I see. Thank you. Are there other questions?
Yeah, Gloria, it's Albert.
Yes.
Just out of curiosity, when you were presenting the next-to-leading part of the chiral Lagrangian, you commented that, well, in my opinion, it's a brutal reduction of the low energy constants. Are well, which is the criteria to do so?
You meant to take that to use
yeah,
to take the same values for the
to equalize
yeah, this is fully justified if you work in leading order in the heavy mass expansion. In that case, it follows from the Lagrangian that they have to be equal. And yes, also because there is no more data. I mean, on lattice, what they calculate is scattering lengths for pseudoscalars. They haven't done the same for vectors, but yeah, taking this leading order, they have to be the same. And also, yeah, well, it translates in my results. No, I get the same results except for the difference of the masses. When calculating everything, the spectral functions, the T matrices, everything, we can see this heavy quark spin symmetry translates into this, that both cases have to be analog, which justifies also this equality of the low energy constants.
Okay, thank you.
May I ask a question? This is Asu.
Yes.
Hi. Yeah, beautiful talk, Gloria. Yeah, I'm just confused a little bit about the values of the masses that, because you are, when you compare with the lattice calculations, so you put in the conditions of the lattice simulation that this is, right.
Yes.
Okay, this is 384. So
yeah,
when you show, I think it's in the 2 slides before, or maybe 1 slide before, and then you change the values of your masses in your theory to put it in the conditions of the lattice simulation. Is that right?
Yes.
Okay, right. 2 slides before, earlier.
This one?
Another one. Here. Right. No. Next one. Yeah, here. Stop. Here.
Yeah.
So, right. So those are the parameters or the values of the masses that you used in order to accommodate the lattice or simulate the lattice.
Yeah, well, these are the values for the quark masses that we include in this calculation of the continuum.
Right. What is this M2 equal to ML? This is the light masses, the up and down?
Yes.
And you put it to 0.
Yeah, in the case of the continuum, we take it to 0, but changing it a little bit, like putting it to 100 MeV, kVs, it doesn't change much. Okay, yeah, basically, you can see that at larger temperatures, the continuum, when you plot it, you can see that it converges to a same. It is independent of temperatures when you go to the high values of this omega. So that's why then when you do the ratio between the correlator and the reconstructed correlator, you go to 1, because the correlator is depending on the value of the spectral functions at very high omegas. So when you do the ratio, because this expression for the continuum, I mean, it's a parameterization.
Yeah, no, you know, I got confused. Because I thought that those values were the ones that you had to put in order to compare with the lattice data.
Yeah, we use these values to compute the continuum part that we put in our spectral function, but the ground state part, we calculated with our effective model, using in our effective model, the parameters are meson masses. So
and then you use directly the ones that
they calculate on the lattice.
Okay, thank you. Right. Yeah. Also, this lattice data, just out of curiosity, this lattice data, do you know if they include the lattice regularization? Because you say that you don't include it in your calculation, of course, but I saw a very regular error bars, like it was just statistics or something like that.
Yeah, no, I think they don't do any corrections.
So neither of, you don't have it, but they don't have it either. Okay. In the comparison, okay. Thank you.
And Asu, may I ask what effect would you expect if they were to include this correction?
Not idea. I mean, in the meson sector, I mean, I have not much experience in the meson sector, and even less in this heavy sector. But it depends. I mean, I don't know how the theory tells you that those observables depend on the lattice spacing. I have no idea. This is what I was asking.
The fact is, on the lattice at very high energies, what they have is that because of this lattice spacing, which is finite, what they have is that this gets distorted somehow. Like there are some peaks and some stuff, which is very difficult to mimic or to parameterize or whatever. But in principle, as at these very high energies, the temperature is a factor that is not that important. When you do the ratio, it might get cancelled. But well, in the case of our free continuum, but in the case on the lattice, these effects we don't know. So they might, these shapes of the ratios might change because of that, maybe.
Yeah.
Hopefully they don't change much, otherwise this would not. I mean,
it wouldn't go to 0, but maybe at not too large taus, they have an effect. I don't know. Yeah, I mean, the ratios wouldn't go to 1, of course.
Are there any other questions for Gloria? Okay, so if not, let's thank her again for the very nice talk. And just to remind you that next week at the same time, in 2 weeks, we at the same time at 11 a.m. we will have a seminar by Samuel Giuliani on nuclear structure challenges for the R process nucleosynthesis. So hope to see you there. Thank you.
Thank you. Bye.
Thank you, Javier.
Bye bye.
Bye bye. Hasta luego.
Adiós.
Adeu.
Adeu.
Molt bé, Glòria.
Gràcies.
Complicat, tot això que fem.